Today I will present our work titled Trust Layers for Automated Bridge Management using Blockchain and Smart Contracts. This work was developed by a research team from 2 universities. The main group is from Politecnico di Torino, Leonardo, Zunino, Valentina, Gatteschi, Marco Domaneschi, and myself. And there is also the contribution of Professor Casas from Universitat Politecnica de Catalunya. So we are a very interdisciplinary research group. We have some structural engineers and some experts of digital technologies and blockchain and smart contract. So the main idea is very simple. So bridge management is becoming more digital, automated, and data-driven, as we saw before. Today we have sensors, so we have a monitoring system, artificial intelligence tools, and digital platforms that help engineers understand the condition of the bridges. But there is an important question, how we can trust the full process, from the data collected on the bridge to the final management decision. I will organize the presentation around the motivation, the workflow, the 4 trust layers that we propose as a workflow, the deployment patterns, and the conclusion. So the goal is to show that trust can be designed in a flexible and modular way. Let me start from the motivation. I don't know why. Sorry. What's happened? Okay. Let me start from the motivation. What's happened? Okay. Sorry. Bridge management is increasingly supported by structural health monitoring, and this system collected data from sensor inspection and structural models. Then usually artificial intelligence and diagnostic tool can process this information and produce indicators, anomalies, or alerts. However, the difficult part is understand how we can pass from the alert to the answer from engineers. So a common idea, sorry, today is very hard.
You just need to use the opposite.
Okay, so a common idea is that the blockchain can solve this problem because blockchain usually creates immutable records. This is partly true, but not completely. A blockchain can prove that a certain event was registered in a certain time. For example, it can prove that one alert was written on chain, but blockchain alone does not prove that the alert was generated correctly. It does not prove that the declared algorithm was really executed or that the declared dataset was actually used. This is the off-chain computational gap. Most monitoring data, algorithm, and diagnostic computation are executed off-chain because they are too large or too complex to run directly on a blockchain. So blockchain can certify that the registration of an event, but we also need a mechanism to verify the chain that produced this event. In our framework, we focused on 4 questions where that you can read here. So where the data altered, filtered, or replaced? Was the expected pipeline actually executed? Was the decision logic consistent and auditable? Can the full chain be reconstructed years later? So before introducing the technical solution, we need to ask what we normally trust in a digital bridge management process. In many cases, we implicitly trust the data provider, the software platform, the algorithm developer, and at least the person who runs the analysis, and the future availability of reports and files in after years. This may be acceptable mainly when there is one organization that manages all this system and control the process. But it becomes fragile when different organizations are involved. For example, imagine a case, in Italy is pretty common, that we have a bridge owner and an engineering consultant, a monitoring provider, a public authority, and all of them need to agree on what happened after an alert. If there is a dispute, as usual, it may not be enough to say the system produced this kind of output. Stakeholders may need to verify the data, the algorithm, the timeline, and the decision process. So these slides show the reference workflows. The workflow starts with the sensors and other sources of information, such as structural data and environmental data, inspection reports and operational information. Then the data and related artifacts are stored off-chain, usually because raw monitoring data can be very large, and after storage, a diagnostic pipeline processes this data. It may extract features, indicators, and usually alerts, and detect anomalies and try to find a problem instead of a breach management. Finally, the process, then we need to define a decision and define the playbooks and approval. And at the end, the process produces intervention evidence, such as inspection reports, maintenance records, photographs, and completion certificates. The key idea is that all these steps should remain connected and verifiable. To support this workflow, we produce 4 modular trust layers. The first layer is content address storage, which gives integrity and persistent references to data and artifacts. The second layer is a blockchain ledger, which provides an immutable governance timeline. The third layer is based on smart contract. We support auditable workflow orchestration. And the fourth one is the certified computation, which provides evidence that off-chain computation were executed as declared. An important point is that these layers are modular, so not every bridge management or each case study situation requires all 4 layers. Layers 1 and 2 are about evidence, anchoring, and governance log. Layer 1 uses content address storage, so in a simple term, a file is identified by its context or an hash. So a dataset, a report, or an image can receive a hash or a content identifier. If the file changes, the identifier changes. So later we can check whether the retrieved file is the original one. Layer 2 uses a ledger to register compact evidence. The raw data are not stored on chain. Instead, the ledger stores hashes, timestamps, actor identities, metadata, and proof references. This creates a tamper-evident timeline. Public, consortium, and private ledgers provide a different level of external verifiability, shared governance, and administrative control. Then we have the third layer that introduces the smart contract. In this framework, smart contracts are not used to replace engineers, of course. They should not decide if a bridge is safe or not, or if they don't design a technical intervention or replace a professional engineering judgment. Smart contracts are a governance tool. They can register certified alert, activate a response playbook, notify responsible actors, set deadlines, and require approval, for example, or register completion evidence. In this way, the process becomes more transparent, while technical judgment remains on human people, so on engineers and authorities. Layer 4 addressed certified off-chain computation, even if data were registered correctly, and even if the alert was recorded on blockchain, we still need to know whether the diagnostic computation was performed correctly. Declared algorithm plus declared data produce declared output. Two possible approaches are the trusted executed environment and the zero knowledge proof. The first one protected execution and evidence about what code was executed, and the second one provides strong cryptography guarantees for all the verification. However, they are more expensive than the previous one, so we can use these only for the third case. So for routine monitoring, can we use just the layer 1 and 2? For the safety critical alert, we can add the third one. And when we have a dispute of or big regulatory reports, for example, for big accident, we can add also the layer 4. So in conclusion, bridge management is becoming more digital and automated, and monitoring system and artificial intelligence diagnostic can produce a lot of outputs, but these outputs must be connected to an accountable management action. So blockchain is not enough because it not automatically prove that off-chain data and algorithm were used correctly. And for this reason, we produce this framework based on content address storage, blockchain ledger, smart contract, and certified computation. As future work, we will focus on sensor validation, inspection data certification, and hybrid TE and ZKP strategies, and integration with monitoring and asset management platform. So the message is that trust should be not only an implicit assumption in automation bridge management, but should be explicit, and we need to understand how we can trust all the process. Thank you for your attention.